PX112. Happy President's Day. So we still have, so President's Day, as you know, is not SU's recognized holiday. So first, I put a survey question for people who would like to help me. So many of you are in organic chem too. So I'm trying to be nice to you. Do you know why I'm being nice? Why I've been so nice this semester? You know? Because one of you will be my physician in the future, could be. And one of you might be my cardiologist or heart surgeon. When the time comes, God forbid, I'll be in an operation room, nervous, and you will be with masks, and I don't want you to remember exam 2. And forget to use anesthesia. Okay, you first. Huh? Oh, OChem. So OChem test is on the 28th. Then this one doesn't apply. Just put random. Is that true? OChem exam is on the 28th, right? Okay. So we'll do the exam on March 1st. I would rather have you, because in the middle of semester, typically there is slump. I would rather have you enjoy your spring break and then come back fresh, okay? How many people have exam on Friday? How many people have exam on Wednesday? It's not the same. Okay, let me think about it. Let me think about it, but I get your votes, okay? If you ask me, I would rather do it on Wednesday but the problem is, the rule is that I can only change the syllabus or policy, but as long as it becomes easier. So I cannot make the exam earlier, I think. At least that's my rule. Okay, so thank you. Any questions? So a common criticism every year is that I put too much materials on my lecture notes and never finish it. That's a valid complaint. Because it's hard to simulate what happened in class. So typically I bring more, and then you just need to delete some slides, okay, at the end. So I'm aware of that problem. So today's class, we have a lot of materials to cover. One is, we will talk about velocity selector, circular motion, mass spec, magnetic dipole, and DC motor. So that's a lot of materials. But let's first recap. So Lorentz force, it's basically the sum of, and I'm just gonna concern about the magnitude here. The sum of the electrostatic force and magnetic force, okay? And this one is Q times E, and VB is, at this point, is Q times V times B, right? And in this class, the order doesn't matter. And your book use this symbol phi, but in more advanced physics, the order matters, and because that thing clumps sine phi. And then this one can be, you can make it more concise by expressing it like this, okay? So it's really straightforward. And then some of you ask, okay, force has magnitude and direction. This expression is only says about the magnitude. The direction follows right-hand rule. And we did a lot of exercise that use right-hand rules. And then before we finish, we discussed that work. So as you can see, people make a lot of money using playing with magnetic field. Mass spec is arguably one of the most powerful techniques in biomedical science. You can ask Mr. Elon Musk whether he make any money playing with DC motor, velocity selector. Mass spec is also related to cyclotron. So magnetic field, magnets or magnetic forces are very useful, but it does zero work because the direction of the force is perpendicular to the displacement. You guys still remember, right? So work is, so right now I'm holding this tissue box, and when I lift the tissue box, I do positive work. The direction of my force is parallel to the displacement. After I put work, this tissue box has what? Potential energy. And when I release it, it turns to mechanical energy and heat. The potential energy disappears, my work disappears. This is similar to what my wife says at home. I don't do any work. Meaning, anyway, work is zero. Work is zero for magnetic field because it's perpendicular, okay? Good. And then next, let's talk about velocity selector. And I use the word tug of war. So there are two forces, and you can tweak the direction of the magnetic field to point towards the same direction of the electric field or the opposite. So velocity selector means you can shoot particles with different velocity, and you can have a small pinholes, basically opening or slit. And then based on the velocity, if it's too fast, maybe it will go to the left. If it's too slow, it goes to the right. And then if it has the right velocity, it will pass the pinhole or opening. And then in mass spec, you use the velocity, this velocity, to figure out the mass over charge ratio. So how to do that? So the nice thing is we have two forces, and the lecture note says that the positive is on the left, the negative electrode is on the right. So the field goes from right to left, right? So let's say, let's only focus on plus charge. Okay. So the force, so Fe will point to the right. Okay. And Fe is equal to Q times E. I'm just gonna write it like this, okay? So without magnetic field, all particles will hit this plate unless it's a neutral particle. Okay, because E is not zero and Q is non-zero for non-neutral particle. So to select the speed, we need a different force. So this one is Fb. Okay, and we learned that Fb is equal to Qv times b, right? And v can be anything at this point. But for particles that pass the pinhole, we select, because we can tune electric field and magnetic field, the v that pass pinhole is critical velocity. Okay. So critical velocity. So at this point, okay. So what happened, what is the criteria for a particle to pass through the pinhole? Other than v is equal to vc. Yeah, so the one guy does like this. What does it mean? Like this? Why are you dancing? So it's not deflected, meaning there is no force. So this one, F equal to 0, for V is equal to Vc if and only if, I guess I can say when F is equal to 0, that means the electromagnetic field is equal to the magnetic field. So the electrostatic field is equal to the magnetic field. And this one is Q divided by E times E is equal to Q, the charge, times velocity times the magnetic field. Oh, I forgot. In order to have non-zero magnetic force, we need magnetic field. Okay. Since it's already crowded, I'm going to use different color. So based on, because I have done the right-hand rule before when I was preparing the lecture notes, the magnetic field points towards you. Okay, so in order to achieve force that points to the right, and if the velocity, the pointing finger point down, then the magnetic field has 2 points towards you. So this one is B. Okay. This B here. Okay. Now we can cancel some term. And I made a little bit mistake here. What is this V? This V is critical. Because if the velocity is larger or smaller, it will either hit this plate or this plate. So Vc is equal to E divided by B. Okay. Which is right there. So it's really nice. By tweaking the strength of the field, we can select the speed, and from that we can run our mass spec. Okay. So I guess we can do the next, this iClicker. Maybe I need to lift this a little bit. So next iClicker. So this is the, okay. So we have this velocity filter, which is a tug of war between magnetic force and electric force. If the speed is larger than critical speed, where the particle will land, to the left plate or to the right plate. Okay, should be pretty easy because I gave you a lot of hints on the slide. Okay, let's spend less than 30 seconds. Fifteen seconds. Yeah. Oh, sorry. Thank you. You should have let me know earlier. So there is, I put one hint on the on this slide actually by accident. Okay, so let's see. Good. So if you don't know physics, well, if you play exam game, then I wrote down like too fast and too slow. So V critical than critical speed. V, like if the velocity is faster than critical speed, then it should hit the left plate. Right? But one way to understand the math or the physics is that the magnetic force depends on the velocity. So the larger the velocity, the larger V, the larger magnetic force. So if the magnetic force wins, instead of the particle goes undeflected, it will point towards the direction of the magnetic force. Okay. So again, on the exam, that hint will not be there if I decide to put that question. And pay attention to the direction of the electric field and the magnetic field. Any question? I have this conceptual question, or basically understanding. This is I went through perusal, and this velocity selector is not really emphasized in perusal, but I'm just curious to test your understanding. So the question is, in a velocity selector consisting of perpendicular electric and magnetic fields, the charged particle speeds are increased or decreased until they are equal to the desired speed. Since that you guys are fast, let's spend 20 seconds on this question. So the question is, do we, I guess another way, like a more daily English way to paraphrase the question is whether we tune magnetic field and electric fields or we tune the speed of the particles. And the question, if it's true, then it's tune the speed of particles. You know, the incoming particle, you play with that, or with selector, you play with the magnetic field direction and strength and the electric field. That's false. Meaning that's option B. I think almost all of you got confused. Okay, just go ahead. Keep on going. Okay, good. So I think 2/3 of the class understand. So for because it's a velocity filter, basically you have a polydispersed, many chemists in the room. You have particles, they have different sizes and different speeds. And then what you do when you filter the speed, you play with the with the strength of the magnetic field and electric field. They have 2 points the opposite direction, otherwise there is no tug of war between the two. Okay, good. Okay, clear. Next is circular motion. Circular motion. So you guys, just to refresh your memory, last semester many of you took Physics 111 with Frank or Dr. Sen. So if you have a circular motion, then the speed is perpendicular or tangential from the circular path. And then there is a centripetal force, which is F equal to what? M times V squared divided by R. Do you guys still remember that? No? Okay, so this is centripetal force. Okay. And it turns out that because the force of magnetic field is always perpendicular, remember, from the speed, then when in the presence of a constant field, in any field, if the particle moves towards one direction, the force is always perpendicular. So it should remind you of a circular motion, because the force of circular motion is always perpendicular with respect to the velocity vector. So this is a video from, I don't know, like 30-year-old video from Caltech that shows when a particle enters a constant field, it makes a nice rotary motion. Okay. I think there is a way you can watch the whole video. So the lecturer is David Goodson. I took his class when I was a student a long time ago. Good. So why this thing is useful? First, we can, so if it is useful because if we fix V using a velocity selector, then by measuring R, we can tell something about mass, and apparently because F has charge, if we fix V, then we can get M divided by Q. So in biochemistry, what people do is people degrade, chop proteins randomly, and then throw that to a mass spec and get different values of M divided by Q. And those are the signatures of a protein. So that's how we do protein sequencing. It's not the best approach, but that's what we have right now. So maybe in your days, in the future, people will use, I don't know, like solid state nanopore or different approaches. But that's what we have right now. Okay, so the first thing that I want to do is we want to measure the radius of the rotary motion or circular motion. So this is the equation. Centripetal motion is equal to the magnetic force. Centripetal force is given by mv squared divided by 2. We can cancel v, like one of the v's. And then if we want r, then r will go this. Right? So basically m times v divided by q times b. Okay. And because q can be negative, b can be negative, and the radius of anything is always positive, so I put this absolute sign. Any questions so far? Okay. How many of you have used mass spec? So that's the notes basically. So next, do you want to do this problem, or do you want me to do this problem? What is this? What is this? Do you want me to do this problem, or do you want to do the problem yourself? The answer is yes. I don't understand. I can do it for you, but you can do it. Trust me. So the question is, what is the angular frequency of the uniform circular motion in previous slide? So what is the expression of angular frequency? Angular frequency is omega is equal to 2 pi divided by period, or 2 pi divided by frequency, but omega r is equal to speed. And I think I give, okay, so what I wrote down is omega is equal to v divided by r. And you know that r is given with this expression. Let's call this equation 1. So v divided by m times v divided by qb. Okay, and v again canceled. So we have q times b divided by m. So this is interesting. Why is it interesting? Omega is equal to qb times m. One, it has m divided by q, which is what we want. But it is interesting because it's independent of r. It's independent of the radius. So the particle that moves close to the center of the circle will move slow compared to the particle that move far away from the center. but they have the same frequency. They finish one revolution within the same amount of time, which is one period. And people use this calculation for, let's say, when they built a synchrotron. And Lawrence was the first one, well, probably, I think he is the one that is credited with the invention of cyclotron when he was at Lawrence Livermore, basically Berkeley. Okay. So I have this iClicker question, so let's do this. So the question is, a charged particle is injected into a uniform magnetic field, so its velocity vector is perpendicular to the magnetic field lines. Ignoring the particle's weight, the particle will, this one should be straightforward. Let's spend 20 seconds. Whether the movement will be straight. The second one is helical. The third option is parabolic. The last option is circular path. So I expect 100% correct answer here. Close. 3 more seconds. Okay, good. So the correct answer is D. So like what we have been discussing is that if the velocity is perpendicular from the magnetic field, which is not drawn here, it's drawn on your notes, then the force or the movement will be circular. Okay? All right. So the direction of the movement depends on the magnetic force here. Okay? V, and depends on the velocity. Let's see how it goes with this problem. Again, maybe I didn't write it correctly. So let's say somebody give you this drawing, and then I can then ask you, what is the direction of the movement? Is the direction clockwise or counterclockwise or helical? What is the answer? I give you a hint. It's a trick question. All right, like 8 more seconds. All right, 5, 3, 2, 1. So what is the answer? So the answer is C. Okay. So because we don't know the direction of the speed, let's say, okay, first, you don't even know whether the speed is perpendicular from the magnetic field. So you don't even know whether the movement is circular. Second, even if you know that the direction is perpendicular, depending on the direction of the particle, meaning like the direction, meaning the velocity of the particle, the movement can be either clockwise or counterclockwise. Okay. That's the answer. Do you want to continue or want to move to the next topic? We have this another iClicker question, and then we will talk about mass spec. So a charged particle is observed traveling in a circular path of radius r in a uniform magnetic field. If the particle were traveling twice as fast, the radius of the circular path would be so V for circular. Let me turn on the iClicker. V is equal to omega times R, and omega is independent of R. So this is the thing that you need to know, and then like V2 is equal, the velocity of the second particle is faster by a factor of 2 than the velocity of the first particle. 10 more seconds. 5, 3, 2, 1. Excellent. So basically, since all particles, they have the same omega, and then if the particle moves twice, and then V is equal to omega R, so in order to speed to double, then the radius needs to double. Good. Any question before we move to mass spec? All right, so next is mass spec. The slide is right there. So for mass spec, we derive for the speed, we can filter speed, and speed is the ratio of both fields. So let me write it again, since it's right now under a different whiteboard. Phi that we select is equal to E divided by B. Okay. So basically, mass spec is we have a velocity selector, and particle can come at different speed. The one that passed through the pinhole has the speed that we want. And in this part of the machine, so in theory, you can have different direction of magnetic field, but typically people use the same direction of magnetic field because it's just cheaper and easier to build. Okay, so. And then based on the charge and the mass, it will move either like this, or if the mass is smaller for the same charge, it will move like this. And then what the engineers do is they have a detector, or in the old days, film, and from the position of the peaks, you can figure out all the proteins in your sample. Okay. So basically, if this is the center, then you get R of this small particle, and this is another R. And radius, and the radius tell us M divided by Q, right? Because V is known. This is something that you can select. It's like adjusting a thermostat. You can select certain things. You can, in this case, scientists or engineers select the speed. Okay. So R is equal to mv divided by Q times B. And then, so M divided by Q, M divided by Q is equal to B times R divided by V. And this V is equal to critical speed, which is equal to E divided by B. So I substitute equation 2 into this equation. B equal to E divided by B times R. R is the position of the peak in a given spectra. So it's equal to B squared divided by E. R. Huh? Okay. So maybe one of you or many of you will be using mass spec, and maybe you will remember this lecture. Any question? Okay. So we still have 15 minutes. Just go. So so far we have, let's say, a given field, and then the charge move towards one direction. Field. So the force points towards us, and the movement is perfectly circular. But let's say there is angle, a little bit angle here, then the movement will be circular. You can decompose this. You can decompose the speed, right? Any speed. Let's say if the speed is points towards an angle theta, you can decompose this vector as vector 1 plus vector 2. So this one is like this. So the horizontal components give a circular motion, but the vertical component, there is no force. So it moves at a constant speed. And then what it does, so if you superimpose circular motion and linear motion, what do you get? Circular motion and linear motion. Amanda. You have circular motion while going up. Yeah, helical motion. Okay, so you get helical motion. And you see this in like North Pole. So I think in the beginning of this section of the class, I mentioned that one of the reasons why life exists on our planet is because our planet has a pretty decent magnetic field. And what it does is that it will trap many charges from let's see if I can. Probably that will not work. It will charge many charges from solar wind. So if this is our planet, and I apologize for my drawing, where is the North Pole? Like geographical North Pole. What is this? What is this? You need to be. You need to help me. So geographical North Pole is here. South Pole is here. Right? But in terms of if we want to model our planet as a bar magnet, the North Pole is actually here, and the South Pole is here. Okay. So as effectively there is this magnetic fields. This magnetic fields always points towards our geographical North Pole. Okay. And then let's say you have a compass here. So compass is basically a magnetic dipole that freely to rotate on a basically needle. The magnetic field always, the compass always align. The compass wants to align to the magnetic field. So this is the magnetic poles of your compass. Okay, this is actually an oversimplification because turns out what happened is, and you should do Google image search for this because my drawing is not that good. So because of solar wind from the sun, it will distort the field. But for this discussion, let's just model solar wind as positive charges that move with speed v. So what happened is many of these charged particles from the sun get trapped here. So it performs helical motion and it's really strong near the poles. It goes up and down and then exit the earth. Okay. So this is how our magnetic fields protect us from charged particles from the sun. Okay. There is a video that is on your notes. Unfortunately, I hide it. So, but it will be on the lecture notes that I will post later today. So it looks like this, and then since physics is universal, it also have been observed in many celestial bodies, such as Saturn. But these celestial bodies need to have good enough distance, meaning like short enough distance from the Earth, and also strong enough magnetic field. So for example, people don't see much aurora on Venus. Good? Any question? Okay, so next we will talk about the electric field, and we will have a demo on Monday. Oh, sorry, on Wednesday. Okay. So so far, what we discussed is charges, either from an experiment, from cathode CRT, cathode ray tube. So if we have charge that stays still and it doesn't, in the presence of magnetic field, it doesn't experience any forces, but when the charge moves, the charge will experience magnetic force. Right? We have done this. But right now, there are many cases, or in most life, in most settings in the world, what happened is a wire with a current. Okay? And then the question is, if you apply magnetic fields, whether you will get any force, whether this wire will experience any force. So what is the answer? If I have a current and I have a magnetic field, will the wire experience magnetic force? I mean, it's right there, right? So so you may think that this one is similar to moving one charge, which I think not a bad way of viewing the problem, but they're actually different. This is like I go to a race car circuit and travel really fast by myself. And this one is like the whole highway move at a drift velocity or a speed. There are different physical processes, but you can think of I as moving charge. Okay? So for Lorentz force for a wire with a current I, the force is equal to, well, let's start with a previous system, which is F is equal to Q times V times B. That is this sine phi. Here, we can say that delta Q divided by delta T. If we multiply, if we divide delta Q and multiply V times delta T, then it's basically I multiply this equation by 1. Anything divided by anything is equal to 1. Anything divided by it's the same thing is equal to 1 times B sine phi. This one delta T cancel. Sorry. That's not, I don't want that. I just undo my hard work. So delta T, I keep delta T. Speed times delta t is equal to constant speed times delta t is equal to distance. I use that funny L. Delta Q divided by delta T is equal to the electric current. So this one is equal to F is equal to I times L times B times sine phi. So this is the second right-hand rule. So instead of so force is still your thumb, your middle finger is still the electric field, and the pointing finger or index finger is the direction of the current. Okay, so from using your right hand, you can figure out the direction of the force. This one is too easy for you. Okay, so this one is very, last time I spent 20 minutes in class doing this problem because I didn't set the problem correctly. So let's do this. I clicker. Do we have 20 minutes? We have 4 minutes. Okay, but you guys are fast this year. So the question is, a wire is carrying current vertically downward. Okay, just in case you forget when you were in Girl Scout and Boy Scout, north points that way, east, south, west, right? A wire is carrying current vertically downward. In which direction will the Earth's magnetic field exert a force on the wire? Horizontally towards the north, horizontally towards the south, towards the east, towards the west, or upward. Okay. And I just send that problem to iClicker. It's not a trick problem. I don't do that. Okay, so 15 more seconds. Five seconds. All right. Let's do this problem together. So the field goes, okay, where does our magnetic field goes, like points to? North, right? Meaning like points that way. North, east, west. Okay. So magnetic field points that way, north. And then I'm using my right hand. So let me just face your direction, right hand. Magnetic field point north. And then the particle move down. So the force points towards east, north, east, west, south. Okay. Did I make a mistake? So either you use this diagram, this one is top view, like when you read Google Maps or any maps. But if you want to use like real life experience, north points that, no. North, sorry, north is that way. Yeah, north is that way, but east, okay, north point that way. So the current move downward, is that right? and then north point this way, and then the force is the thumb, the direction of my thumb, north, and then this one is east. What? Yeah, where? Sorry. So we can do top view, north, east, west, south. Okay. Let's say you see from this is top view. Okay, north, east, west, south, and then the current points down. Right. So the current point down. So my index finger points down. Magnetic field on our planet always points north. So the force points east. Right? When you look at down, north, east, west, south. So yeah, meditate on it, and then we can discuss on Wednesday. So let's recap. We covered a lot of things today, and we'll continue on Wednesday. See you on Wednesday.